So we hypothesize that if we have an isolated system, that the system will reach equilibrium when the entropy of the system is maximized. Okay? To be precise, let me at least define for you what it means to be an isolated system. So for an isolated system, what we have is that the number of molecules in the system, the volume of the system, and the internal energy of the system, all those things are constant. So for an isolated system, we have a constant NV and U system. Okay? And so for a constant NV and U system, it reaches equilibrium when entropy is maximized. Okay? But that begs the question, what happens if we don't have a system in which all of NV and U are constant? So what about if we don't have an isolated system? What would our equilibrium criterion be then? Okay? All right, in that case, to at least identify, when other types of system would reach equilibrium, we could think of a couple of examples, right? And so let's say our system doesn't have constant NV or U. Instead, other things are constant. Okay? And so the first other type of system that we'll consider is one in which the number of molecules are still constant, the volume is still constant, and temperature is constant, but not necessarily internal energy. Okay? All right, and so at least what I want you to picture in your mind is, let's say we just have some sort of system that looks like this, right? And the system is surrounded by a reservoir. And that reservoir is very large, such that the temperature of the reservoir is going to be constant at all times. Okay? All right, and so we have a system that's surrounded by a temperature bath, if you will. And stuff is happening inside the system that may initially change its temperature by some infinitesimal amount. But because it's in this constant temperature reservoir, what happens is that if the temperature of the system changes by any little bit, there's going to be heat going into the system, right? So you could have heat going into the system, or maybe there's a reaction going on to the system, inside the system or something, that causes the temperature to increase a little bit. In that case, you would then have heat leaving the system. Okay? So heat, doesn't matter which direction, but let's just say heat is either entering or leaving the system. Okay? All right. And so the system's in some sort of temperature reservoir. The reservoir itself is at constant temperature. And we'll also say that the temperature at the boundary of the system is also at T reservoir. All right. In fact, we won't call this T reservoir. We're just going to call this T. Just a general T, like that. All right. And so this is our system. But if we consider the universe in this sort of situation, the universe, remember, is our system plus the reservoir that it's in. Okay? And the universe itself, right, since it encompasses everything in here, you could think of the universe as an isolated system, right? And then that our actual system of interest is just a part of that universe, and the reservoir is another part of that universe, okay? All right? And so if we think of the universe will reach equilibrium when the entropy of the universe is maximized, okay? All right, so that criterion will still exist. But what we want to figure out is, if this is our system of interest, when will we know when this is at equilibrium, right? And so the system here is something we're considering to be a constant NVT system, okay? And so let's figure out what the criterion would be for our system that's within the universe to be at equilibrium, okay? All right, and so to do this, let's think about the energy and entropy balances of both the system and the reservoir, and then the universe. And so for our system, delta U sys, in the energy balance, there's no change in volume, but we do have, heat going into or out of the system. And so we're just going to call that Q total. So this is the system EB. For the system entropy balance, we're just going to say the entropy of the system changes. And we're just going to call it delta S. All right? So for the reservoir energy balance, we're going to call this delta U reservoir. And whatever heat either leaves or goes into or leaves the system, that's going to be equal in magnitude but opposite in sign from the heat that enters or leaves the reservoir, right? And so the change in internal energy of the reservoir is going to be equal to negative Q total. Okay? When we think about the entropy balance for the reservoir, it's delta S res, right? And one thing I kind of forgot to mention here is, for the setup of this problem, we're going to be considering at least that for the individual system and the individual reservoir in the entropy balances, we're going to be kind of taking a hypothesis that all these processes are reversible, similar to what we did at the beginning of chapter 4. Okay? And so if we take a look at the entropy balance for the reservoir, and we're assuming that the change in entropy of the reservoir is a reversible process, the entropy balance would simplify to this, right? Which is the delta S of the reservoir is just the negative Q total over the temperature at the boundary between the system and the reservoir, which we're just calling T. Okay? All right, but what we know is that we have negative Q total here, and negative Q total, or Q total, we know is equal to delta U system. And that's based on our system energy balance. And so what we could do here is that in the reservoir entropy balance, we could just plug this in. And so what we have is negative delta U system over T. Okay? All right, and so this is the entropy for the system, and this is the entropy for our reservoir. And so to figure out the total change in entropy of the universe, it's just delta S system plus delta S universe, or delta S reservoir. From the reservoir entropy balance, we could plug this result in. And we could simplify the equation or rewrite it like this. Divided by t. Okay? Alright, so I put them on a common denominator, and I factored out a negative sign to flip these positions. Okay? Alright, and so we find that the change in entropy of the universe is equal to this statement here. And the reason I rewrote the statement like that is because if we take a look at what's in the numerator, we have delta U minus T delta S. And if you remember from chapter 6, when we did the Legendre transforms to develop new fundamental energy equations, we developed one that was known as the Helmholtz energy. And the Helmholtz energy was equal to U minus Ts. And so what we have here in the numerator is the same thing as saying delta A for Helmholtz. So this would be A of the system. And so what we find is that delta S universe is equal to the negative of delta A of our system divided by temperature. And what we know is that the delta S of the universe can only be greater than or equal to 0. Okay? Alright, and so what this tells us, because there's a difference in signs between each side, is that as the Helmholtz energy of our system decreases, the entropy of the universe would increase. Alright, and so what we get for systems that are constant molecules, or constant N, constant volume, and constant temperature, if a process is going to be a spontaneous, irreversible process, what we would see is that the Helmholtz energy would decrease. So spontaneous, irreversible processes. And then, we see that delta A is going to decrease for a spontaneous, irreversible process. And then when S universe is maximized, that is, when the change in S universe is equal to 0, we would see that our Helmholtz energy is going to be minimized. Okay? And so, just to summarize what we developed, if we have a system with constant N, constant V, and constant temperature, it's not an isolated system anymore, but we could still develop a criterion for determining when the system reaches equilibrium. And that criterion would be that the Helmholtz energy of the system is minimized.